You know how some numbers in science just feel weird? They're not neat and tidy, but super specific, almost random looking. Well, it turns out every single one of them has a fascinating story. And today, oh man, we are tackling a huge one.
All right, let's just jump right in. Look at this thing, 6.022 times 10 to the 23rd. Now, you probably recognize this as Avogadro's number, and yeah, it's a huge deal in chemistry, but come on, let's be real. It looks totally random, doesn't it? Like someone just pulled it out of thin air.
And that right there, that's the big question we're going to unravel today. Why that number specifically? I mean, why not something, simple, like a trillion? Or just 1 times 10 to the 23rd? Where on earth did this super specific number come from, and what makes it so important?
Okay, so to get to the bottom of the number, we've actually got to start with the idea behind it. And that idea is a little something called the mole.
So, what is a mole? Well, the concept itself is actually way simpler than you might think. It's really just a counting word. Think about it. We have a pair for 2 things, a dozen for 12 things. A mole is the exact same idea, just for a ridiculously large number of things. Specifically, 6.022 times 10 to the 23rd of them. And we're usually talking about atoms or molecules here.
But here's why it's so genius. It's way more than just a giant number. The mole is like the chemist's secret weapon. It's this incredible bridge that connects 2 totally different worlds, the microscopic world of single atoms, which we can't see, and the macroscopic world of our labs, where we can, actually weigh stuff in grams. It's how we count atoms just by weighing them. It's amazing, really.
And here's the magic trick in action. Let's take carbon, right? Look it up on the periodic table, and its atomic mass is about 12 AMU. That's atomic mass units. Now here's the cool part. If you get 1 mole of carbon atoms, that's our big number, 6.022 times 10 to the 23rd of them, they will weigh exactly 12 grams. See that? The number 12 stays the same. We just swapped the tiny unit for the big one. It's the perfect conversion factor between the atomic world and our world.
Okay, so we've got the mole down. It's a bridge, a counting unit. But we're still left with that weird number. So where did it come from? Well, to answer that, we have to go back in time. And trust me, the history here is way more of a tangled mess than you'd expect.
And right off the bat, here's plot twist number 1. The guy the number is named after, Amedeo Avogadro, he never calculated it. Not even close. As this paper from 2011 points out, he had the brilliant idea that made it all possible, but the actual number crunching, that happened way later thanks to a whole bunch of other people.
I mean, this wasn't a quick discovery. This story plays out over almost 100 years. It all kicks off in 1811 with Avogadro's big idea about gases. But then, nothing for decades. It's not until 1865 that a guy named Johann Loschmidt even gets a ballpark estimate for how many molecules are packed into a tiny space. Then you've got other scientists like Horstmann and Than building on the idea. The word mole itself doesn't even exist until 1900. And get this, the name Avogadro's number wasn't used until 1908, more than 50 years after Avogadro was gone. It's a total team effort spread across generations.
So, if Avogadro wasn't the guy, who was? Let's zoom in on that critical moment. How did someone finally put the puzzle pieces together and get the first real number?
It basically came down to 2 key puzzle pieces from 2 different scientists working decades apart. First, back in 1865, Loschmidt figured out how many gas molecules you could cram into a really small space, just 1 cubic centimeter. Then, much later in 1889, another scientist, Karoli Thon, figured out the opposite. How much space a whole mole of gas would take up, a much, much bigger volume.
So you've got the number of molecules in a small box, and you know the size of the really big box. What do? Well, you just multiply them. The math is surprisingly simple. You take Loschmidt's density of molecules and multiply it by Pfann's total volume. The units cancel out perfectly, and boom, you're left with the number of molecules in 1 mole. Their answer was 4.09 times 10 to the 22nd. Now, that's not what we use today, but for the late 1800s, that is an absolutely incredible first step.
Of course, science didn't stop there. Over the next 100 years or so, we got way, way better at measuring this number. Scientists came up with all sorts of clever new experiments, like this one here called electrodeposition. You basically pass electricity through a solution and count the atoms that stick to a surface by measuring the change in mass and charge. It's super precise, and just one of many ways we honed in on the value we know today.
But the story doesn't just end with a more accurate number. No, there's one final, amazing plot twist, and this one happened just a few years ago, in 2019. Okay, hang on, because this part is genuinely mind-bending. For the longest time, the old way of doing things was to define a mole based on something physical, how many atoms were in 12 grams of carbon. That meant Avogadro's number was something we were always trying to measure more accurately. It had a tiny bit of uncertainty. But in 2019, the scientific community did something radical. We flipped the script completely. We decided to define Avogadro's number as an exact value, period. No more measuring, no more uncertainty. It is now a perfect, fixed number by definition. And now, we actually use that perfect number to help define what a kilogram is. We turned it from a measurement into a measuring stick.
And that, right there, finally brings us back to our big question from the start. Why the weird, specific number? And the answer is, it's basically a historical accident. It's a leftover from how we started measuring things. We humans invented the gram based on, a certain amount of water, long before we had any clue about atoms. Avogadro's number is just the number of atoms that happens to line up with our old, human-made definition of a gram. We defined the gram first, and this is just how many atoms fit. It wasn't chosen to be weird, it was discovered.
So, let's pull all this together. What does this whole journey mean? Why does this matter?
First off, the mole is the absolute bedrock for chemists. It's how they count atoms by weighing them. Second, remember that Avogadro's number wasn't some flash of genius from one person. It was built over a century by a whole team of scientists. Third, that seemingly random number, 6.022 times 10 to the 23rd, is the magic key that links our everyday scale of grams to the invisible scale of atoms. And finally, and this is the big one, it's not just a measurement anymore. It's now a fundamental constant of the universe, a pillar that helps hold up our entire system of measurement.
Think about that journey. This number went from being a fuzzy measurement to being a perfect ruler we use to define our reality. It really makes you wonder, doesn't it? What other numbers are we measuring today that in the future will become the fundamental rules we live by?